Okay.
All right, we're back again. The world famous Harley Smith. I'm the organic mechanic with Kelp4less.com.
Mhm.
And just before starting recording on this session, we were talking about some questions we've gotten from customers. And I think it came out we need to address the element of iron. Iron often overlooked. What source of iron? How to use iron? And what makes iron work better in your system? It's probably a key element. Um, and I know Hardy can really go into detail on this one. The benefits of the iron, how often it's not looked at as a key element, but I think we need to focus on that a little bit as a key element and how to make it work better. So I'm just going to throw this iron ball over to you. You catch it and see what you can do with it.
Okay. Well, iron is often the limiting factor in soil, and in hydroponics, we definitely it can definitely be limiting. Let's talk
Yeah.
about hydroponics first, but when I do a hydroponic nutrient formula, I do I provide iron as a chelate, an iron chelate, because iron is very pH dependent. In fact, if in soil without any help from microorganisms that produce chelates, without any help from the plant making organic acids, you'd have to have a pH of around 3, that low a pH, just for iron to be available. So in hydroponics, we provide iron as iron DTPA. It's a synthetically made organic chelate. And as you know, chela means claw, right? So a chelate is an organic molecule that attaches to a mineral like iron, like a claw. It holds it tightly enough so it doesn't lock up or oxidize, but loosely enough so it's available to the plant. And iron DPA is a fairly stable um, chelator. So we use that because otherwise, if the pH is above, say, 6.5, the iron starts to become available. If the pH is above 7.5, that's just barely alkaline, then all of the transition metals, iron, copper, manganese, and zinc, they start to become unavailable. But iron is the one that's the most sensitive. It oxidizes, it turns into rust when it's exposed to oxygen, and then I can't take it up. So in hydroponics, all the other transition metals I do as EDTA. Still a pretty good chelator, but iron is, I definitely want to do iron DTPA. I've even worked with some growers that would have their own tank, their own tank for injecting just the iron DTPA because it's that critical to get the right balance with that. So that's it for hydroponics. It has to be a chelated form, and the same is true in nature, but it's done by organic chelates that are made by nature, by
Uh-huh.
microorganisms in itself.
Yeah, biology. In the agricultural world, we see that all the time. Again, I seem like I always talk about this, but um, we're really big into soil testing to kind of see what we're starting with. Soil pH, the available nutrients, the available minerals, and things like that. And it seems a lot out west, there is so much iron in the soil, but yet our plants still come deficient in it. And
Mhm.
in an agriculture setting, it's hard to address that again if you don't prepare for that. So we go back to the additions of many biostimulants and the biology and just the biology we can establish around the root zone of a plant to help make some of those natural biostimulants to help deliver that nitrogen to the plant. Um,
Mhm.
it's a common issue uh, that we try to deal with almost every crop season sometimes, and a lot depends on the environment too. The temperature of the soil that really regulates a lot of biological functions that go on, and the biostimulants that are being created just in the overall environment of a growing season. So it can go up and down as well. So it's challenging. It's very challenging sometimes. Boy, it'd be nice just to um, have a drip system in every plant in the field, kind of like how we do in hydroponic. That would make things easier, but it is a struggle.
Hmm. Yeah, iron is very important. Iron is actually a cofactor for the production of chlorophyll.
Hmm. Hmm.
You know, if you start getting a iron deficiency, you'll see yellowing, usually at the top of the plant in the new growth, because it's an immobile element. And it's part, not just to make the chlorophyll, it's part of the electron transport chain that's
Hmm.
used to make ATP, to make energy available to the plant, both in photosynthesis and in cellular metabolism. So it is a limiting factor. It is a critical, it's uh, out of all of the trace elements, the micronutrients, the plant needs the most iron and it has to be available. And I'm with you. I was out west, volcanic soils loaded with iron. And then over and over again, I'd see the iron deficiency in my leaf tests. So yeah, we need to make it more available. Now, plants themselves, you probably know this, but plants themselves have strategies to make iron available. If in some grasses, they literally make siderophores and exude them from their roots. And siderophore literally means iron carrier. It's one of the best chelators of iron in nature. Now, microorganisms, some of the plant growth promoting rhizobacteria, they also make siderophores right on the surface of the roots. So they help solubilize the iron and make it available to the plant. Now, now the grasses, they make their own siderophores. Now the other plants, the dicotyledons, our garden plants, they don't exude siderophores. But what they'll do is exude organic acids, like citric acid, from their roots. And then it makes the surface a little more acidic, so the iron's a little more available, and it chelates. It's a weak chelator. So it doesn't lock up, so the plant can take it up. And then once it's inside, iron is inside the plant roots, it combines with citric acid, and that's how it's transported throughout the plant to be used. So in the old days, before we had chelates, synthetic chelates like in hydroponics, we used citric acid to to uh, to chelate the iron citrate. But it's not as stable. It kind of has to be in nature's kitchen, real time, manufacture just in time to take it up. So yeah, so iron is that important to the plant that they've developed. Different plants have developed different strategies. But either way, I think the greatest thing is the microbes that make the siderophores. They make the organic acids. They acidify the root zone right on the rhizosphere, and they definitely, and they even make some of the organics like the fulvic acid. Yeah, maybe you could speak to fulvic acid a little bit, humic and fulvic acids and their role in the uptake of iron.
Yeah, you bet. So um, I just want to back up just a little bit. A common iron we like to use out here is iron sulfate, just because it is
Yeah.
acidic.
Hmm.
And anyway, it goes back to the things that you said, the acidic form and things like that. Now, with the addition of fulvic acids, that's very important too for iron uptake. And again, if you look at your you know where chelation comes from, chelated, the claw. I like to think of fulvic acid as a big or a large lower pH claw that has a lot of fingers that can attach many elements to it for nutrient uptake into the plant. And so we like to tell our customers look at humic acid as a high pH claw and a fulvic acid as a lower pH claw. And so they're both beneficial at different times for different elements. And I'm sure you've seen this in hydroponic too, just the those organic acids, the fulvic and humic, they're kind of like a nature's chelator. in a
Uh-huh.
lot of different circumstances. So very popular in the farming agriculture world to help bring up those micronutrients into the plant. A very good tool to have. Two different claws, so to speak.
Yeah, yeah. There's the fulvic acid is a little lower molecular weight molecule, and the fulvic acid is a higher molecular weight, but they do work together. They work together in nature. You know, the large ones, the humic acid fraction actually makes a bridge between the clay particles in heavy soil and the
Yep.
nutrients, like a finger, but it makes it more available to the plant because those heavy soils can hold the nutrients so tightly that it's hard for the roots to take them up. And even with if you have excess organic matter too, you overdo it with organics, that will start to do the same thing. It'll bind them too tightly, where the humic and fulvic acids help make them more available. But one of the science things I'd like to say specifically about iron again, circling around, but when you look at fulvic acid, you see that kind of an orangish color to it. That's iron. So it's already has iron in it. Chelated iron is in it. And also, it's a scientific fact that humic and fulvic acids literally activate enzyme called H plus ATPase in the cell membranes. That's a proton pump. So what happens is it stimulates the plant to exude protons from the inside of the cell membrane, inside of the cell, to the outside of the membrane. And those positive ions make it acidic. The more positive ions, the more acidic. So, but then the inside of the cell becomes more negatively charged. The outside of the membrane becomes more positively charged. So it's like a battery. The potential energy across the membrane increases, and the plant literally uses that energy difference, potential energy, to take up iron and other nutrients too, not just iron. But iron is a key because it's harder for the plant to take up. So wow, nature with nature can do this without our help, and it has. And microorganisms in the soil help it even more. The pH in the root zone, the rhizosphere, could be 2 or 3 points lower than the bulk soil. Very key. And I think really, I mean, when I attribute a lot of the benefits of biostimulants and microbes to the trace ability of plants to take up more trace elements, turn on enzymes in the plant.
Oh, Harley, that was a deep dive. I mean, that is some in-depth information. And I just want to
Yeah.
touch on one point you made. We get so tied up in the pH of our soil, and we have to have the perfect pH of soil, and it does help if you can adjust those things. It does help, especially on a small scale, container gardening or or whatever. But in agriculture, we have to make the bed first for the soil microbes and the root zone to work together because it's not about how much sulfur we apply to the soil to adjust the pH or how much burnt hydrated lime we add to the soil to change the pH. The plant roots will control that for their environment. So if we can make
Mhm.
the bed for the root zone, with biostimulants and things that support biology and support that root zone, the plants usually figure this out. I mean, they control the pH. We don't. They control it in a setting like that. If we again set them up for success.
Yeah. Yeah. It's all about the root zone. And it's what it comes down. You want to, if you have the ideal conditions at the root zone, and plants have, there's iron, what they call iron homeostasis, that they control the amount of iron. They know when they need iron, they're going to do things, they're going to respond to take out more iron. If they have enough iron available, they do things so it doesn't build up too high. Plants have their own regulatory system that is
Yeah.
just actually amazing. Um, but yeah, they can control their the environment of their root zone. And one thing, here's a good one for you on iron is some of the microorganisms. We talked about organic acids and acidity, but some of the organizations like Bacillus subtilis, GBO3 substrate, it literally makes volatile organic compounds and makes Virginia, not Virginia, Texas Tech did a big research study on that. And they found that some of those volatile compounds, even if the microorganism doesn't touch the root, it's not even on the root. It's like a bouquet of aromas that can activate up to 600 different genes in the plant. It's
Oh,
communicating with the plant and helping it to make some decisions. Now, one of those volatile compounds actually affects the iron homeostasis of the plant. It tells the plant to take up more iron. Why would a microorganism do that? Well, if the plant takes up more iron, it's going to make more chlorophyll. It makes more chlorophyll, it's going to harvest more light energy and make sugars. Some of those energy, carbohydrates you'll use to grow. Some of it will be shipped to the roots. Some will be exuded from the roots to feed the microorganisms. So there's this whole cycle going on, a communication between the plants and the microbes, between the microbes and the plants, uh, to be able to not just survive, but to thrive. And that, to me, is an exciting. I think the microbes and some of the things that you're working on, Brandon, are literally the future, the new frontier in in sustainable agriculture. Because if we can work with nature, nature's already been doing it. If we can work with it in a intelligent way, the plants will be able to, I don't know, I'm getting a little on my soapbox here, but we'll be able to feed the world in an environmentally responsible way.
yeah, a lot of factors involved in that too. And it seems like with all the good we're trying to do, we still have practices that hurt us, that set us back, that slow down that. And there's a lot of factors involved. But I totally agree with you. A plant wants to be healthy, and a plant wants to stay alive, and a plant wants to produce more chlorophyll and more sugars because it's got a lot of friends down in the root zone it's trying to feed too. And so
Hmm.
we look at a plant, and oftentimes we get carried away with what's on top, and oh my goodness, just we get so one directional in our thinking on what's on top. Let's just take a little bit of that thinking and take a look at what's going on underneath and how that can really affect what we see with our eyes. And so, using the microbes and the biostimulants and things like that, for some people, it's it's a hard concept to understand sometimes, and and I'm sure you've experienced this. Like you've told us stories about uh, going to going to Europe and seeing the hydroponic operations there, and them doing the initial testing on biostimulants and all the research they were doing a long time ago. But they did that because they had to see it for themselves, and you had to see it for yourselves. And so don't get too tied up on what's going up on what you see up top. That is important. But underneath what we don't see is such a large makes such a large contribution. And boy, you're helping people understand that. I hope we're helping people understand that. And let's just do what we can to make the best environment for them. That's
Yeah,
my number one thing I think I tell people. Can we make a good environment for the red zone to get started?
yeah,
It affects so
that's
much.
it. Yeah, I guess we're starting to run out of time here, I think. Oh, we have a
Yeah.
couple more minutes, But one thing too that's overlooked is how those trace elements like iron and copper, manganese, and zinc, how important they are for stress tolerance in the plant.
Mm,
When the plant's under stress,
yeah.
the reactive oxygen species, free radicals, are generated. Or even when you're pushing the plant in a in an indoor system, with light and CO2, they make free radicals. And one of the worst free radicals is called superoxide. And it attacks the cell membranes, the lipids, the cell membranes, the chloroplast membranes for photosynthesis, bleaches out your plant. It attacks the mitochondrial membranes. That's where metabolism happens. When there's too much stuff, now plants will make an enzyme called superoxide dismutase to protect the plant against superoxide. It breaks that free radical. But if there's too much stress, the plant can't make enough superoxide. But guess what? We found out combination of humic acid and kelp, here we go again, stimulates the plant to make 50% more superoxide dismutase to protect the plant
50%.
against heat stress, salt stress, drought stress. Is there any problems with drought stress ever in the summer?
Oh boy.
UV stress from too much sunlight? Yeah,
Oh yeah.
but that molecule, it can make literally stimulates the plant to make 50% more superoxide dismutase. But that enzyme has to be turned on either by an iron manganese complex or a copper zinc complex. So if we have microbes that are aiding with the uptake of those elements in it, that the the superoxide dismutase molecule is turned on, one molecule can do over 1,000 chemical reactions per second inside the cell. If those trace elements are unavailable, then it's doing 0 chemical reactions per second. That's why I think they did the combination of kelp and humic and folic acid work better than either of those just by themselves because they're stimulating production of a molecule and activating that molecule. And that's just one part. There's you work with nature, there are many, many beneficial side effects that we as scientists
Mhm.
haven't even anticipated, haven't even
Mhm.
thought of yet. But nature has all the answers if we know where to look. And we're starting to get a clue. We're starting to get a clue. And if we can just take that to the next level and then to the next level, yeah, we can literally, make the world a better place.
Well, you're dialed in today, Harley. Man, you brought it hard and heavy with this iron. You showed up with 1,000 pounds of iron and just whacked us with it. Yeah,
Yeah.
that was good. That was a deep dive. Boy, so appreciative you shared this knowledge with me, with whoever watches, whoever listens. I mean, this is incredible that you take the time to do this, and we appreciate that. And that was fun. That was a heavy hitter.
Okay. Well, iron is just one of those limiting factors. I don't care if you have organic soil or you're doing hydroponics, iron is still limiting. So everything we can do to help the plant take up adequate, sufficient iron, the better. I guess I'll close with one thing you mentioned, Europe. When I was over there visiting the greenhouses one time, I noticed that they had a big, one of them had a big bed of river gravel, and they were spraying water from the well when it was came out of their well. They were spraying it in a mist over the river gravel, and I said, what's that? What are they doing? Oh, they were taking the insoluble iron out of the water. When the iron is in the well, it's in a soluble form. But as soon as that hits the, the ferric iron, ferrocene, as soon as it hits the air, it oxidizes and turns to rust, and then it's unavailable. So they were spraying it onto the gravel, the water. It was removing the insoluble iron, and then they were adding the chelated iron on the other side that was available to the plant. Because that insoluble iron too, you've seen it. I mean, well, you see it in my house, that's for sure. It can start to even clog up emitters over time. That rust, that rusty stuff. So they just remove the insoluble and add
Wow.
the soluble.
Yeah. Wow, that's unbelievable. I've never heard of that. That
Yeah,
is phenomenal. Well,
it's
we're going to have a
simple.
lot of people spraying rocks now.
Yeah, you'll see the surface of the gravel will start to turn orange, but
Yeah.
that's what you want because that orange on the surface of the gravel isn't orange in the surface of your drip emitters.
There you go. Fantastic information once again.
Yeah, that's all I have today. I think that was quite a bit to
Oh boy.
to
Yeah,
digest.
like I said, that was a deep dive and you nailed us, literally. An iron nail. You nailed us.
Yeah, and don't just throw iron into your reservoir. That's a myth. Yeah, let's take some iron nails and throw it in there and see what it does. Yeah, great, good idea. No, bad idea. Actually, I wouldn't even call it bad. I just say useless, maybe bad,
Useless.
potentially bad.
Yeah, listen to Harley first. Listen to Harley first before you go around doing that. He'll set us straight. Well, I appreciate your time once again. This was fun.
Yeah, it was. Okay, but I guess we'll talk some more later, and I'll see you next week. If
See you
there's
next
any
week.
yeah,
We
anybody
may
out
have
there that
to,
has questions,
yeah, we may have to switch our day next week. I'll be on the road, I think, the day we do this podcast, but I'll stay in touch with you.
okay, yeah, I'm flexible whenever.
Okay.
Okay, let me know, and we'll reschedule.
Okay.
Okay, talk to you next week.
Once again, thank you. And always a pleasure.
Okay, see you later. Bye bye.
All right. Bye bye.